afternoon session of the summer school. I'll introduce Professor Sebastian Haro, which will talk to us about the conceptual analysis of black hole entropy in string theory. As always, for clarificatory questions, you can book your chat during the talk. For more structured questions, we'll wait for the end of the talk. I should tell everybody that you don't need to write the whole question in the chat. Just book your spot and I'll give you the slot to talk directly to Sebastian. So you don't have to waste time writing the question down. And this said, I'll leave the stage to Sebastian, and on you go.
Okay, thank you, Mirko. Yeah, thanks to the organizers for the invitation to this talk. So we'll talk about conceptual analysis of black hole entropy in string theory, and this is based on two papers that we wrote with Jeroen van Dongen, Manus Visser, and Jeremy Butterfield, which appeared in Studies last year. And here's the motivation for this work. I will present the microscopic state counting of the extremal black hole performed by Andrew Strominger and Kumran Vafa in 1996 in its contemporary context. So our motivation is, in the first place, historical, trying to understand the history of the subject. And we will also analyze the argument, the structure of the argument, which is rather complex. So in particular, we aim to identify the various intertheoretic relations on which this argument depends, and those are a duality and the linkage relations. So I will get back to this. And then to make clear why the argument was immediately recognized by the string theory community as a successful account of black hole entropy. The discussion that it engendered, especially ADS-CFT, further developments, and then at the end, depending on time, I will have some further philosophical questions that arise naturally from this calculation. So, for example, what is the black hole in some sense the same physical system as the Dbrain for which the Debrain system for which the calculations are being done? Those sort of questions I will get back to at the end. Here's an outline of the talk. It has 3 parts. I begin with some background in string theory. Then I will present the calculation itself conceptually, so I will not show any details about the calculation. Also, this particular calculation actually builds on several previous papers, so I will try to give like a conceptual schema of how the calculation goes, what are the different elements involved. And then I will go into the more philosophical questions towards the end. But first, a few comments about black hole entropy in general. So recent empirical discoveries, including using gravitational waves and the Event Horizon Telescope, of course, suggest that black holes do exist in nature, that we can measure some signatures of them. However, there are still many things that we don't understand about black holes. For example, space-time singularities, the information paradox, and the black hole entropy, which will be my topic. So theoretically, a key proposal is due to Jacob Bekenstein in 1973. He proposed that black holes actually carry entropy. There was also work around the same time, a little bit later, by Bardeen, Carter, and Hawking. And the temperature of these black holes was famously calculated by Stephen Hawking. So Bekenstein had a rough formula, an estimate for this formula based on some qualitative arguments, and then Stephen Hawking did a field theory calculation where he was able to find the precise coefficient. So here is the formula, which is well known to all of you. For the black hole entropy, so it's proportional to the area, and all the other constants are fundamental, well, are constants of nature. So Boltzmann's constant, the speed of light, Newton's constant, and h bar. The area is the area of the black hole horizon. Now, in this talk, we will be concerned with black holes in the specific framework of supergravity, and these were found in the 80s by Gibbons and Hull and Callan, Myers, and Perry. But then in 1996, Strominger and Waffa posted this very short article. It's really just 9 LaTeX pages, with the first microscopic calculation of the entropy of a black hole in string theory. There had been studies of black holes in string theory before, but none of them was really so precise that they could calculate the entropy from within string theory. So this provided, in the eyes of many string theorists, a first microphysical account of black hole entropy, and it was taken to confirm the Bekenstein-Hawking formula. It quickly became an important result, a well-known result in string theory, which also spawned many other developments in the subsequent years. So, for example, it was followed by Ed Witten's duality conjectures about various dualities existing in string theory and supergravity theory, and also Polchinski's suggestion or rediscovery really, of some objects called Dbrains. So both of those developments were in 1995. Sorry, these were prior developments that led up to the Strominger-Waffa calculation. So the Strominger-Waffa calculation was made possible, as I will review, by these two papers. So these are two central papers in the study of the Strominger-Waffa black hole. So, like I said, there was a fast pace of developments around this period, so leading to this calculation. Now, the microstate counting is perceived by string theorists as one of the major successes of their theory, and it has been highly cited. So it is considered that this was an important step towards better understanding of black holes in string theory, even if the main questions are still unanswered. But this was a step perceived as a step forward. The Strominger and Waffa's calculation. It played a key role in the developments leading up to the ADS CFT conjecture, which was in 1997, towards the end of 1997. It's now 25 years old, and so it has been studied by physicists from many different angles, and there have been many different generalizations for many types of black holes and Debrain configurations. So we feel that after 25 years, that the time is right for philosophical and historical analysis of this material. Now, like I said, the Strominger-Waffa paper is a brief statement of our result, including references. It is 11 pages. It was written during a frantic period of activity, so building on previous results. So some of it is, I would say, it is written in a rather technical or even cryptic language, at least for the outsider. And so for this reason, I will review some of this material. Again, not in a detailed manner, but more at the conceptual level. So like I said, our project aims to give a historical philosophical analysis of the argument and to outline what its role was in the history of the subject. And we hope that there are many open questions, so we're really just kind of opening the ground for this particular paper. So there is a lot to be done in this area. So we will focus on two questions here. So one is, why did the Strominger-Vafa calculation have such a persuasive power in the mid-90s within the string community? So that it was seen, like I said, as a macroscopic derivation of the Bekenstein-Hawking formula. And so to see that, we have to see how it involves all the developments that people in string theory were familiar with at the time. So we will factorize the arguments in various factors, so that from a string theory perspective, it becomes, in hindsight at least, a very natural and almost unavoidable argument. And also, second, what was its significance for the further development in string theory? And I will be a lot briefer on that, and especially in leading up to the ADS-CFT correspondence. So much so that nowadays, when people think about the Strominger-Vafa calculation, they normally don't think of it in terms of the original calculation, but they actually think of the ADS-CFT reformulation, which in a way is simpler, and which I will also briefly mention. So here's the argument in a nutshell. At least its parts. It consists in four parts, four theories that are being related. The first is supergravity theory, which is Einstein's theory of gravity with a number of specific matter fields, bosonic and fermionic fields that are added, which follow which are allowed by supersymmetry. The second theory will be a theory of strings that interact in with higher dimensional objects called Dbrains. So I will get back to this. Then the third theory will be a theory describing describing the dynamics of the Dbrains themselves, the infrared limit of the Dbrains. We will go into this. And then there is a fourth theory, which is not used explicitly as part of the calculation. It's not needed as part of the calculation, but it is mentioned, at least the spirit of it is mentioned by Strominger and Vafa in their various, in some of their broader comments and speculations about, the significance of their calculation for information loss and so on. So this is the conjectured M theory that underlies the dualities that are used in the calculation. So there are conjectured dualities between the string theory realizations of theory 1 and theory 2, so supergravity and the string theory. And also there are linkage relations among them that I will go into. Now, the Strominger-Vafa paper presents a calculation of the microstates for the system of Dbrains. So the calculation is not done in the supergravity theory, rather it's done for the Dbrains. And that will be actually quite important, so that one can actually do a calculation, because that's a regime where one can make use of weak coupling. So weak interactions and short distances. The calculation is then extrapolated and compared to the Bekenstein-Hawking formula for the black hole, which is then in a different regime applying to supergravity, so at strong coupling and at large distances. So if these are the four kind of elements of the argument, then here are the two main assumptions of the argument, or the main two ingredients. So one is duality. There's a duality between open and closed string theories, which is close to the relation between theories 1 and 3 here, so between supergravity theory and the Dbrains. And then, and so in particular, that goes through Polchinski's work on Dbrains. I will get back to this. A duality, remember that a duality is basically a one-to-one correspondence and isomorphism between two theories. And so here there is, in this case, there's not an exact duality, but there is a conjectured approximate duality that can be used. And then the second important element, this is really the key element, is the use of supersymmetry. All of these systems are supersymmetric, and that is what justifies the comparison of the entropy at different values of the relevant quantity. So if one kind of gives up supersymmetry, then you could say that there is no reason why this should work if there isn't supersymmetry. The justification for the calculation is that there is a certain amount of supersymmetry preserved within the theory. So this involves what are called extremal black holes. So those are black holes whose electrical charge is equal in certain units. It's equal to the mass. One of the first generalizations that I will discuss is to non-extremal black holes, so the situation where its supersymmetry is actually broken. But like I said before, there is no a priori expectation or a priori reason why this should have worked and why it worked as well as it did. And I would say that this is still this is clearly still an open question today. So much for kind of the general introduction, the structure of the argument, the different parts that go into it, and the two main principles that justify, at least from within the string theory perspective, what one is doing when one is comparing these different systems. Now, I want to go to some of the details of the string theory, because these are really needed to understand what goes into this calculation. Like I said, 11 pages, but there is a whole sea of previous work that goes into that. So there are many concepts. On the other hand, most of them are not difficult concepts. They can be explained, at least intuitively, if one wants to go into the technical details. Then that, of course, that's much more involved. But here I will look at this from a more conceptual side. So here's a list of all the concepts that I'm going to go through now. Some of them are related. So you see things like open and closed strings, which are two different types of strings. Type A and to B, string theory, again, different types of string theory. So some of these are just laying out the basic theories that I already mentioned. Some of the states, the BPS states that are within the theory. The Dbrains, of course, very important. And the theory that goes with the Dbrains. So that's the basic sketch of this part. So let me go into some of the basics. Open and closed strings, and this is very intuitive. You can think of a closed string as drawn here as really a piece of rubber that is vibrating in a certain number of dimensions. In this case, in 10 dimensions. So it's a vibrating piece of string. Of course, there's a classical description. We want the quantum mechanical description, where this becomes kind of a harmonic oscillator that can interact. So there are closed strings, but there are also open strings. And these open strings, well, in the theories that we will look at, they always have to end on something. So there are other string theories where these open strings can live just by themselves and can move freely in space. But for us, in the theories that we will be looking at, these are which are the 2A and 2B theories. The open strings always should end on these hyperplanes, which are the things that we call Dbrains. So Dbrains are hyperplanes on which the open strings can end, and they are sources for the non-abelian charges that are carried by the string. So the open strings carry non-abelian charges, Yang-Mills type of charges that are sourced by these Dbrains in very much the same way as, say, a quark is a source for a non-abelian or an electron is a source for the electromagnetic field. So that so far as the Dbrains goes, and the open strings, and then the closed strings, they are the carriers of the gravitational force. So the gravitational force is related to the excitations of the closed strings. So when we talk about open versus closed strings, you could say that this is roughly the distinction that we are familiar with between, on the one hand, the gravitational force, and on the other hand, the nuclear forces, the weak and the strong nuclear forces. Now, there's some fundamental constants that go with together with the string. One is the string length, fundamental string length, which is the typical length of a string, also related with tension. A notation that is often used is alpha prime. So alpha prime is the squared of the open string length, and so in the point in the limit that the string length goes to 0, this becomes kind of a point particle. So that's a point particle limit. Of course, you always have to do that. Always have to set alpha prime to 0 related to the other typical length scales that you have in the problem that you're looking at. So we'll go into that later. And then the second one, second coupling constant, is the string coupling constant, Gs for G string, which measures the strength of the interactions of the strings at the level of the strings themselves. So you can think of this. We are here interested in quantum mechanical strings. So we have Feynman diagrams for, in this case, for closed strings. Here you see at the bottom, and so each of these vertices comes with a factor of Gs, or in the case of a closed string, Gs squared. So here we have two things. On the one hand, here we have different dependencies of the G string, so different powers of the G string. Here we have, on the vertical axis, we have the point particle limit. Those are the two things that you can kind of vary in the theory, two parameters. And like I said, you always vary them relative to something else, relative either to some external length scale in your problem, or some other, in this case, some other energy scale in the problem. So that's the distinction between open and closed strings, which is quite central to all of this. There is a further distinction between type 2A and type 2B string theories. It is somewhat important for the calculation, but it will not be very crucial. So it is more of a technical distinction. So these both theories can have open and closed strings, and the main difference between them is in the type of Dbrains that they can have. So the type 2A string theory can have Dbrains of even dimension, and the type B string theory, type 2B string theory, can have Dbrains of odd dimension. So that's the main difference, space-time dimension. Here are some more technicalities, but I will actually jump through them. Also, when you look at the original paper by Sturminger and Waffe, they don't really specify which. They also at some point jump from one theory to the other, but they just assume that the reader is familiar with that, so they don't mention that really. Maybe not in a footnote or very briefly, but this is one of the things to be aware of, that there are two different theories involved. Okay, then that is introduction to string theory. Let me say something about the semi-classical limit of supergravity. So how do we get supergravity as some type of limit of string theory? Well, we can do that when we go to low energies or large distances. So we typically look at large systems, like, for example, a black hole of a large mass, so large Schwarzschild radius, and in that limit we can approximate the main features of the theory by supergravity theories. And so large distance here really means taking square root of alpha prime, so that the string length divided by, again, r, which is the typical scale of your system. So say this could be the horizon radius, or even better, the kind of typical length scale at which you probe the black hole, or another typical system. So this is something that we very often do in physics. We introduce some kind of typical length scale with which that we use to probe or to test our system. Now, the type 2A, type 2B string theories require 10 space-time dimensions for their mathematical consistency. So these supergravity theories that we're talking about are also 10-dimensional, both of them. We go from 10 dimensions back to 4, or later back to 5, by compactifying on certain Calabi-Yau spaces, certain internal spaces that I will mention. But those details will not be terribly relevant for what I will have to say. So there are two key developments, like I mentioned before, that led up to that made possible the Strominger-Vafa calculation. And these go under the name of the second string revolution. Both of them were in 1995. So the first is due mainly to Ed Witten, but there were other people involved as well. Where in early 95, he gave evidence for a series of dualities connecting the various string theories with each other. So I've already mentioned, these open, closed strings, type 2A, type 2B string theories. So there used to be 5 string theories at the time, and there were also these supergravity theories. And the conjecture was that these 5 string theories and 11-dimensional supergravities, that all of those theories were related by a number of precise dualities that one, at least in some limits, he could give evidence for. Now, what was kind of the main piece of evidence, or the main insight actually that led to this conjecture? Well, it was that Witten realized that there was a class of states in string theory that are very unlike the usual states. So normally people do perturbation theory in string theory. We think of the string as a harmonic oscillator, right? And we perturb around the harmonic oscillator. So we do small perturbations. But Witten realized that there were some states that were in the theory that you could describe some features of, but they could not be reached by this kind of perturbative argument. They were what we call non-perturbative states. And their distinctive feature was that their mass is inversely proportional to the string coupling constant. So the mass is proportional to the charge, to the electric charge, and inversely proportional to the string coupling constant. So you see that in the perturbative limit, where GS goes to 0, these states become very massive. So they decouple from the theory. If you think of this in a typical renormalization group way, then these massive states, you don't see them at low energies. Even though in some cases they may be important, there may be non-perturbative effects that one has to take into account. So what was special about these states? Well, they have the minimum mass possible for a given charge in supergravity. So states could have more mass. They could be more massive. Usually they are more massive, but they cannot be less massive than this. So there was a certain inequality that follows from supersymmetry that one could prove, and this was the minimum that one could have. So within string theory, sensible states should satisfy this inequality, and these are kind of the ground states, you could say, of the theory. And so they cannot lose energy. They are in that sense stable, energetically stable states, because they have the minimum energy. So they do not Hawking radiate, and they have 0 temperature. Yet their entropy is non-zero, as we will see. So they could be the quantum equivalents of degenerate ground states. So some ground states that have a degeneracy that gives rise to a non-zero entropy. And the second thing is what I already said. They become infinitely massive at weak coupling, and that's why you don't see them in perturbative string theory. They are called BPS states because this condition, this is the BPS condition, that the mass is equal to the charge That goes back to work earlier, much earlier work by Bogomolny, Prasad, and Sommerfeld. Okay, so the rediscovery of Dbrains in open string theory. So as I have, this is the second, I have described the first development in '95. Now the second development that made the Strominger-Vafa calculation possible, rediscovery of Dbrains. Polchinski had already toyed with Dbrains in 1989, together with some other people. But now in '95, after Witten's talk, he realized that these Dbrains were actually important in string theory. So he writes in his memoirs that he wrote in 2017. So Polchinski unfortunately passed away fairly young, a couple of years ago. He was able to write these memoirs where he writes, at the end of Witten's talk, Mike Green and I looked at each other and said, that looks like Dbrains. It was a shockwave for me and the rest of the field. I have been living with Dbrains for 8 years, but never taking it too seriously. For almost everyone else, it was a new thing. String theory had Dbrains as well. Okay, so he developed, found further evidence for the existence of and some of the properties of these Dbrains. In particular, he could find a mathematical description of these objects within string theory, something that Witten had not done, and he could reproduce some of their properties that Witten had said they should have. So he calculated the mass that Witten had obtained by other arguments, and that agreed with Witten's result. Also, the number of the types of supersymmetries that he found. Also, these Dbrains. Remember the Dbrains I said at the beginning, they are sources for certain non-abelian charges. So they did the right job in that way. They couple to the appropriate gauge fields on their world volume. And this actually goes back to much earlier work in the 1970s by people like Mandelstam, et Hooft, and so on. And you could find some of those properties now here also within the Dbrains. And okay, and a number of other things that he did in that paper. Okay, so these are kind of two pillars of this launched the second superstring revolution, because this made possible a number of further theoretical developments. So now that there were these dualities around that could be used to find in a regime where one calculation is very difficult, you can go to a dual picture where the calculation becomes doable, and so on. So you can kind of use these tricks to find out more and more information about the theory and kind of cross-check several results. And then also these new objects within the theory that in a way completed our view of the theory, because string theorists had worked with perturbative string theory, but of course anyone who works on gauge theory knows that at some point you need to also go into things like solitons, monopoles, right? So you need to look at the non-perturbative or non-linear structures that are within the theory, and that's what Dbrains did for string theory, like in a way analogous to what they do for gauge theories. So a further distinction that will be important. So Dbrains, the D stands for Dirichlet, which is the kind of boundary condition that the open string satisfies on this hyperplane. Remember, we said that the open string ends on the hyperplane. That's a Dirichlet boundary condition. So the endpoint is fixed to that hyperplane. The string cannot oscillate in the transverse directions. That's different from other types of boundary conditions, like, for example, a Rubin boundary condition. So that's the boundary condition. Now, the P-brains, P stands for the number of spatial dimension of a brain. A P-brain is a completely different thing altogether. So a P-brain is an object in supergravity that looks like a black hole. So it's the supergravity equivalent of a black black hole. So it's the closest thing to a black hole in supergravity. And those were discovered quite in the of string theory, and actually much earlier than all these developments. But they did play an important role in Witten's calculations. So they are solutions of the low energy limit of closed string theory. So it's important to distinguish those two because p-brains belong naturally to supergravity. They are solutions of the equations of motion of supergravity, whereas d-brains are quantum mechanical objects. They are part of the string itself. They also have to do, insofar as the supergravity is a low energy limit of string theory, they belong to different sectors of the theory. The p-brains have to do with the closed string theory, which has to do with the gravity, whereas the open strings have to do with the open strings and not the closed ones. So Polchinski wrote, as an instrumenter has reminded me, Gary Horowitz, and I had lunch together nearly every day for 3 years without realizing that their black p-brains and my d-brains were the same. So I think this nicely summarizes this slide, that these were really two different things, and even these researchers for years, they were working on p-brains and on d-brains, and they were having lunch and seminars together, and they didn't realize that these objects were somehow, at least that's the conjecture, that these objects were ultimately the same or had the same origin. Okay, so that is, those are still some of the prior developments. Now,
Sure, if it's me, I think there's a few.
Discovery was an extension of this open-closed string duality. What is open-closed string duality? Well, it's a duality that was.
So your audio cut off for about 30 to 45 seconds. Can you please start again just from the very start of the slide when you first opened the slide?
Yeah.
Thank you.
All right. So Polchinski generalized open-closed string duality. He realized that there was an extension of this duality which was already known. It could be extended now to d-brains. So here is the basic duality. So this is actually Polchinski's own argument. So if we have d-brains, parallel d-brains, then we can think about the interaction between these d-brains. In principle, it goes via open strings, right? We said the open strings, they are the endpoints the d-brains are the endpoints of these open strings. So there will be a force that is mediated by these open strings. But he realized that this you can reformulate this in terms of a closed string that is now exchanged between one d-brain and another. To do that, what you have to do is you have to look at this as a space-time diagram where time kind of goes at 45 degrees, and you can reformulate this amplitude over here it just gives you this amplitude on the nose. So an open string amplitude gives rise to a closed string amplitude. That's a generalization of the duality that was already known, now generalized in the presence of d-brains. Now, this is an approximate duality, and it relates two systems of interest: the open string d-brain system and the BPS black hole states in the supergravity limit of the closed string. So these 2 points here are the specific way that Polchinski's duality argument figures in the Strominger-Vafa argument. So I'm going to develop now these 2 points. So here's the picture, right? So we're going to think of the open string, which is this side over here, as, well, in terms of really a stack of d-brains, and we're going to have an extra d-brain with which we probe the stack of d-brains. And then we do this open string duality, And then we go to the closed string side, where what we have at low energies is something that looks like a black hole. It's the Dbrain. So let's look at the left-hand side in a little bit more detail. So how do we describe these Dbrains and their interactions? Well, there are two ways. So let's focus on the dynamics close to the Dbrains, rather than looking at the long distance phenomena. Let's look very closely to the Dbrains. So what you find is then something like this. This Dbrain over here is on top of all the others, right? All these Dbrains are stacked together. Well, this is maybe too wide, but all of these are closely together, and we decrease this distance so that basically all of our Dbrains are very closely stacked together. So this R over alpha prime becomes small, much smaller than 1. Now, Witten showed that the dynamics of this system is given by a Yang-Mills type of quantum field theory that lives on the world volume of these Dbrains. So you could imagine that, for example, the world volume, if these are 4-dimensional Dbrains, right, that fill the entire space, then this would be a 4-dimensional 3 plus 1 4-dimensional Yang-Mills theory, or Yang-Mills theory in that case. In other cases, for other dimensions, it is some conformal field theory. So he found that within field theory, within conformal field theory, there are techniques that you can use to describe the dynamics of the open strings, at least when we are very close to the Dbrains. So that's the left-hand side of this open-closed string duality. Let's now see how we can go to the right-hand side, how this was found. So there were a number of works that illustrated the relation between this theory on the Dbrains for various Dbrains and supergravity. So for example, so there's the CFT, right, that lives on the Dbrains, and it describes the interaction between the Dbrains. Now, the infrared regime of that world volume theory describes the short distances in string theory, like I said before. And we will see in a moment that this describes the
Sebastian, I have a question from Eric.
Yeah, Sebastian, just a clarificatory question. So you mentioned that that Witten showed that on the previous slide that the short length couplings can be the dynamics are given by this Yang-Mills type QFT, and you mentioned that it can be thought of, at least in some cases, as 4-dimensional decomposed as 3 plus 1. Did you mean that it actually has a Lorentz geometry and it's 3 plus 1 in that sense?
Yeah. This is indeed all Lorentzian geometries. Yeah.
And is that imposed by hand, or does Lorentz geometry fall out naturally?
Yeah, this follows naturally from the string theory. So we begin with an open string theory, which is in 9 plus 1 dimensions. So in 10 dimensions, but one of those dimensions is time. So there is a time dimension always within the string theory. And then when we focus on the system of these Dbrains, then we compactify to a lower dimensional theory, which still has the 10 dimension on it. Yeah.
Okay,
so it follows naturally from the fact that these open strings, from the boundary conditions of the open strings. Yeah.
And that 9 plus 1 is actually a Lorentz signature.
Yeah, it's a Lorentz signature. Yes.
Okay. Thank you.
Yeah. Okay. So now this fact that we are probing short distances in the system of the Dbrains, and that gives us the infrared regime of the world volume theory, that is surprising because normally when we think of short distances, we think of high energies, right? That's what people do at the LHC. Why do you need such a big accelerator? Well, because you want to probe the shortest distances, so you need to accelerate to high energy. But here, it's the opposite. So we're looking at very small systems, and we do that through the infrared limit of this Debrain theory. So that's surprising. This is called the IR-UV connection. And this is ascribed to the extended nature of the strings between the Dbrains. Now, for reasons that have been worked out by Tov many years before, in the presence of Dbrains, the relevant coupling is not the string coupling, but G times N, where N is the number of Dbrains, which is also the electric charge of the Dbrain, since the charge is quantized. So the effective coupling of this theory is not GS, but GS times N, and this will actually be important later. Okay, so that finishes the first introductory part. All of this goes into the argument, although actually I have already kind of almost spelled out the left-hand side of the argument. So what I now have to do is to say a bit more about how the right-hand side, how the gravitational part of the argument, so this part around here works. Okay, so to carry out the entropy calculation, Sherman-Jan and Waffe need to establish this connection between, on the one hand, the black hole solution, which is sitting over here, or actually the Dbrain that looks like a black hole, and the appropriate configuration of Dbrains, whose charges are the black hole charge, which is sitting over here. Now you see I've filled in some of the parameters here, so this we have already encountered, namely the distance at which we probe the Dbrains, and here we have the hoofd coupling, so the GS times N. So when we go from this side to the right-hand side, we will also increase the coupling. So let me now present to you the right-hand side of what system did they choose for their supergravity theory. Well, the supergravity black hole that they looked at is the 5-dimensional Reisner-Nordstrom extremal black hole. They chose 5 dimensions just for convenience because it was too hard to do this in 4 dimensions, so they did this in 5 dimensions. This is a solution of type 2a supergravity on a 5-dimensional manifold. The 5-dimensional manifold, well, the details are not really important. It's a K3 times S1. K3 is a certain Ricci flat space, and S1 is the circle. So that circle will actually be somewhat important, but the K3, not really. It is important that it is flat. The basic idea here is that we begin in 10 dimensions, right? And by compactifying 5 of those dimensions, we end up with a black hole with a configuration of P-brains that look effectively like a 5-dimensional black hole, even though, actually it's a 10-dimensional configuration, but at least to a good approximation, we can think of it as a 5-dimensional black hole. Now here's the metric, the 5-dimensional metric of this black hole. So you see that it has this unusual double pole, right? So if you compare this with, for example, the Schwarzschild metric, that's quite different. The Schwarzschild metric has only a single pole. So this gives this particular black hole this has some special properties that I will mention in a minute. So the horizon radius, which is given here, and the black hole entropy are given by the solution in terms of the P-brains. So the charges of the P-brains, which are given here, right? So this particular configuration of P-brains has 2 electric fields. So that's why we get a QF and QF. The details don't really matter for now. It's just 2, like having 2 photons. And that gives you the horizon radius and the entropy. Now, this configuration is valid, so that the supergravity description is valid only if we have a large black hole. If we have a Schwarzschild radius that is much larger than the string radius, the string length, and also weak string coupling, right? If you translate that in terms of the charges, well, there is some condition that the charge satisfy. Again, it's not really important. Those are technical details that I plan to suppress in this talk. So the important message here is that there is this 5-dimensional Reisner-Nordstrom black hole, and that its parameters are supplied by the underlying Dbrain configuration of the supergravity theory. Now that was the supergravity description. Now we need to link this up with some kind of Dbrain over here, right? So some string theory configuration. So what is that? So we call this, well, the heart of darkness, the Dbrain configuration. Again, for this Dbrain configuration to be valid, there is some regime of parameters that you need to satisfy. Again, the string coupling needs to be weak because we need to be in weak string coupling. On the other hand, also the 't Hooft coupling needs to be weak so that we can actually use perturbation theory for the conformal field theory on the Dbrains. Now, Strominger and Waffe considered, like I said, a configuration of Dbrains in type B, which means compactifying. So it's actually you need to take a combination of D1, D3, and D5 brains. So basically, they are taking not just one type of Dbrain, but they are taking 3 types of Dbrains and intersecting them in various ways, such that they have a common S1. So this S1 is common to all 3. And then there are some other 2 cycles and 4 cycles. These are, again, technical details that are not going to be important. I just flash them here so that you are aware of them. The important thing is that they, by doing this, by getting this common S1, we're going to get the right type of conformal field theory with the right amount of supersymmetries, the right amount of charges. That's the bottom line. And because they intersect along a large S1, the S1 is common. This is a large S1. The other cycles are small. So we compactify on all the other ones, whereas this S1 is large. So naturally, if you think of dimensional reduction, Kaluza-Klein reduction, you're going to end up with a theory on the large S1 because all these internal space are going to disappear. So we end up with a theory that lives on the S1 and also on the time direction. Okay, so the Dbrain calculation. What is the calculation that you can do for the Dbrains now? So again, what is the theory on the world volume of the Dbrains? It is the relevant world volume. So the relevant space that we have is this common S1 times the time direction, because the A3, the internal space, is small. So the theory is a 1 + 1 dimensional conformal field theory, a 2-dimensional CFT. In these CFTs, you can count states. The degeneracy of the states with fixed energy is given by the Cardy formula. So the Cardy formula gives you the degeneracy in terms of the energy and the central charge of the theory. The central charge is roughly the number of elementary degrees of freedom of the CFT. Now here, the identification of these parameters is as follows, and this is actually quite non-trivial, and I will not go into the details, but to see these identifications, you actually need to go to previous work by Kumbrum Waffe. I will not go into that. The energy is the charge. This is basically the BPS condition. But then this is non-trivial. The central charge is, well, given by the square of the charges. So that comes from previous work by these gentlemen. So this is relating, you begin with a system of Dbrains, but then you end up with an effective theory on the intersection of the Dbrains that describes the Dbrains on that intersection. Now, after filling in the values for the logarithm.
Sebastian, we have another question from Eric.
So, yes, very, very quickly, is there any intuitive way to see why the energy depends only on one of the electric fields and not on both?
Probably there is, but I would have to think about that. I don't have an answer at the moment. So, yeah, there should be one, but we can get back. Okay, so the statistical the statistical mechanical entropy for the system, given by the logarithm of the number of states, so the degeneracy of the states at fixed energy, is given by the Cardy formula, and it takes this form over here. Now, Sherman and Buff assume that the Cardy formula is still valid if the central charge is much larger than 1 and QF squared is much larger than 1, in which case the above, so this formula over here then matches the Bekenstein-Hawking entropy formula, where the area of the horizon is matches the charges. Again, so this is using the area for the corresponding black hole. So we have now linked up the system of Dbrains to the corresponding system of P-brains and their black holes, and now we match the area. So this is the basic Strominger-Vafa result. It's this formula here. It relates the Boltzmannian entropy for the Dbrains to the Bekenstein-Hawking entropy. Now, how do we know? There are various approximations that go into this. How do we know that this has the right approximations? And again, there is a lot going behind the scenes here. So basically, supersymmetry topology guarantees that in addition to taking C much larger than 1, that one also extrapolates from weak coupling to strong coupling. Because like I said, the Debrain calculation is valid at weak coupling, which is the regime in which you can do field theory calculations. You can do conformal field theory calculations. You can calculate something like, the degeneracy of a number of states. You can solve the Schrödinger equation and calculate the number of states. You can do that at weak coupling. At strong coupling, that's where the supergravity calculation is valid, because then you have a large black hole. And actually, it is supersymmetry that ensures for us that this number is going to stay invariant. So the number of BPS states is independent of the 't Hooft coupling. So that's one of the fundamental results about supersymmetry. The supersymmetry algebra, seen as one of the defining features of our system, right? That supersymmetry algebra implies this BPS bound, and that is going to imply that the number of BPS states is simply fixed. Okay, so here's so that was kind of the argument in a nutshell. Now I'm going to explain it a little bit more conceptually, see what is going on. So the derivation depends on linking the strong coupling supergravity description over here with the weakly coupled Dbrains over there. Due to supersymmetry, the degeneracy of the Dbrains is independent of this variation. So even if we don't have a strong coupling description of the Dbrains, still the number of BPS states should be is the same, is protected as people in the jargon of string theorists. So here's we can summarize then the calculation in this way. We started here, right? We said, well, there's a corresponding system, black hole system that we can draw using open-closed string duality. And if we want to calculate the entropy here, the entropy here, what we do is we do a calculation here. How can we do a calculation here? Well, we go to this Debrain theory, close to the Dbrains, where things actually become tractable. And then we use supersymmetry to actually link up this calculation with the corresponding result over here. Now, what is the role of this other corner here? Well, actually, this is the corner where the coupling is strong, but also we are at short distances. So we probe. So this is kind of, quantum gravity, if you will, in some sense, at least. That would be the expectation that this is, of course, the motivation for, at least part of the motivation for doing some of this. So here, the conjecture by Witten was that there existed a theory that we don't know. We don't know almost anything about this theory. It's called M theory. M theory stands for, well, various things. It could be membranes. It could be matrix theory. It's a conjecture theory, but valid at small distances and strong couplings. It's unknown. Witten made some conjectures about what this theory could be like, some of its properties. He argued that at strong coupling type 2A string theory develops an 11 dimension, so that if actually we begin with type 2A string theory, well, somewhere over here, right? Somewhere maybe over here, so at short distances, and then we go to shorter and shorter distances. Eventually, we will develop an 11th dimension, which and then another theory appears, which is this mysterious M theory. Now, like I said, M theory did not play any role whatsoever in the calculation by Strominger and Waffa, although it is kind of just the motivation. Okay, so far this is kind of analysis of what is in the papers, how does this fit historically with the previous work. Now I want to say a little bit more about how was this judged by the string theories that were working in this field in around 96, 97. So they quickly noticed that there are two idealizations that one is making here, which are both of them undesirable. So one of them is supersymmetry. We are assuming supersymmetry. The black hole is extremal because of the supersymmetry of the states. We need these BPS states because they are the states for which we can actually do calculations. In some sense, they appear to be fundamental within string theory because they have the minimum energy. So they are ground states. But on the other hand, from the perspective of kind of macroscopic black holes, the black holes that our colleagues might be interested in, we don't want supersymmetry. So we need to go beyond, at least if we want this to be relevant, not just within the string theory framework, but more generally, we need to go beyond the extremality limit. And then the second idealization is the higher dimensions. This was done for 5 dimensions. Again, we don't live in a 5-dimensional world. So how do we do this for 4 dimensions? I should say that, well, the second has been overcome. The first, as I will tell you in a minute, there are improvements, but it is still one of the open questions, at least in some important respects. So let's see how this was improved upon. So one first generalization, actually, you can see the fast pace of this field because like 1 month after, or 1 month and a half after this paper, Callan and Maldacena came up with a new paper where they generalized this to the non-extreme, well, to the near extremal case. So they considered a 5-dimensional black hole with a mass m that exceeds the extremal value by a small amount. So again, it is, we begin with kind of the maximally idealized case, and then the next best thing you can do is the harmonic oscillator, the linearized case around this free case. Okay, so the mass now is the charge plus a small deviation. Okay, so now the outer and the inner horizons, which used to come together, are not the same anymore. So now supersymmetry is broken. Now, in spite of that, the microscopic and macroscopic calculations that you can do within the Dbrain setup on the one hand, and on the other hand, within the supergravity, still agree. So at linearized level, the entropy, the correction for the entropy that you get is goes with the square root of the additional mass that you put in, derived by the original extremal mass. And then now you have a non-zero Hawking temperature, which is again proportional to the square root of the extra mass. They also calculated the radiation rate within the string theory setup, so not within the supergravity, but within string theory. And that confirmed the black body spectrum predicted by Hawking. The mechanism for evaporation is that open strings on the Dbrain collide to form closed strings, which are then detached from the Dbrain. So on the Dbrain itself, these open strings can kind of meet and then form, two open strings can form a closed string and then leave the Dbrain in the form of closed strings, and that becomes the Hawking radiation. So that is one departure from supersymmetry. Now, Maldacena and Strominger did a first generalization to 4 dimensions. So now, in order to do that, they had to introduce even more charges. And now they got a black hole with 4 different charges. And that is basically the reason that it was hard to find before. So Strominger and Vafa couldn't do that calculation. And then subsequently, there were very many other generalizations to rotating black holes with mass, charge, and spin. Also black holes in M theory, at least in the conjectured model for M theory. So they found that if you wrap an M5 brane on certain cycles, then you effectively get, well, on a 5 cycle, then effectively you get a D0 brane, a particle, something that looks like a particle, and you can calculate, so it looks like a black hole, and you can do the entropy calculation. You can actually calculate also quantum corrections to the black hole, to the Bekenstein-Hawking area law, and that agreed with the supergravity calculations. So they could match the M theory calculation with the supergravity, with the one loop supergravity calculation for that. And then very quickly, in 2 years after ADS-CFT came along, and then the original Strominger-Vafa calculation was embedded within that framework. I'm not going to go into all those details. So again, there have been very many generalizations. So it's a huge field. Like I said, many open questions still open, both from the physics side. So people are still working on this in string theorists, but also from the more philosophical side. Lots of questions to be investigated further here. Okay, now I want to go to some of these questions. And like I said, I will only scratch the surface, I believe. So what are the natural questions that we have? I mean, one set of questions I've already asked. One set of questions is, how trustworthy is this calculation? How idealized is this setup? How can you improve that, and so on? Well, that's one set of questions. The type of question I'm interested in here is less technical and more conceptual in terms of, well, what are the role that is played by these dualities? What are the different kind of points of view that we have, right? So we have all these different theories, and we do all these different approximations. What is actually, what is it that you actually see? Which is the theory that of all these four theories, which one is valid when, and so on. So those kinds of commonsensical questions, and all of them are related to dualities. So is the black hole in some sense the same physical system as the Dbrain system to which it is compared? Or is it a different system? Is the black hole in some sense maybe emergent from the Dbrain system? So those are two first questions. Now, our view is that one should be cautious about this, and we joined some of, well, there have been several cautious views in the literature. So for example, Smolin dubbed the view that the two models describe different systems. He called this a pessimistic point of view. So the point of view that the Dbrains and the supergravity solution, that these are actually not the same system, but that they might be different systems, that they are different systems, even if you take into account that, you know, the coupling is different. So it's not even the same system at different values of the coupling, but it's two completely different systems altogether. That's what he calls the pessimistic point of view. The relation between the two systems is probably an accidental result of the fact that both have a lot of extra symmetry. So on the one hand, he calls the Strominger-Vafa perhaps the greatest accomplishment of the second superstring revolution, but at the same time, he wonders whether a genuine explanation of the entropy and temperature of black holes had been provided, since the piles of brains are not black holes because the gravitational force has been turned off. And this is a very fair comment, because indeed you have to, like I said, I mean, you have to tune the coupling, right? We go from strong coupling where we cannot do any field theory calculations. We need to go to weak coupling. That's what he means by turning it off, so making it zero or weak. Jacobson Jacobson actually is more optimistic than Smolin, but he still has some doubts about the broader relevance of this type of calculation. So he said that before ADS-CFT, there was this wonderful state counting, but the connection for me with black holes was really indirect because they were weak coupling phenomena, and there wasn't actually a black hole there, it's just a stack of Dbrains. If you turn the coupling constant up, non-renormalization theorems from supersymmetry tell you that the state counting result must be preserved, and thus one could make a black hole. So this is, in Jacobson's words, what I said before, right? So we use this weak, strong relation, and we use supersymmetry to relate the calculations in the two regimes. But actually, in the regime in which we do the Dbrain calculation, there is no black hole, there's no supergravity type of black hole there. And so even though Jacobson thought that from the point of view of calculating black hole entropy, that might be just fine, but that does cast doubts about the relevance for things like, for example, the information paradox for black holes. That was Jacobson's view at the time. This is from an interview that we did with Jacobson. At the same time, this was part of he was telling us how he went from, thinking that information was lost inside black holes to thinking that information might be or is probably preserved. So he was also describing kind of his own struggles with that, because one of the things that changed his mind was not actually the Strominger-Vafa per se, but the ADS-CFT. But it started already with the Strominger-Vafa. But like I said, I'm not going to go to focus on the information paradox here in view of time. Okay, so Rovelli also has made some comments about this. Basically, he points to some similar facts. So he also points to the fact that in loop quantum gravity there is an analogous calculation that one can do, and okay, that both are honest calculations of the entropy, and that both of them kind of fall short of giving you kind of a first principle calculation, an honest quantum gravity calculation, or better said, first principle quantum gravity calculation of the Bekenstein-Hawking entropy. Okay, so those are some cautious views which actually collect some of the facts that I mentioned earlier about the various approximations, dualities, and also idealizations that are involved. Now, how are the two systems related? So these are the questions that we were more interested in. So what arguments are there that could relate the two systems rather than just the entropy? So could we say that there is, apart from a relation between entropies, which is secured by supersymmetry, but is a purely, you could say it's a purely formal fact of supersymmetry, can we also say that there is some relation between the physical systems? Now, if there were an exact duality between the open and the closed strings, then we would be in much better shape, because the dualities are often taken to be indications that two systems are the same or strongly resemble each other. But even that is not true in this case. We don't have an exact duality. We only have an approximate duality. So for that reason, from the beginning, we shared this previous caution. There are only perturbative definitions of superstrings, and the present consensus is that there is an exact duality between open and closed strings, that there isn't an exact duality. It's not to be, there isn't one, and it is not even to be expected in the Schrödinger-Vafa calculations. There are other setups, like, for example, ADS-CFT or other field theories, where you might find such exact dualities, but not in the original Schrödinger-Vafa case. So that's in some way bad news if you want to be a believer in that these two systems are the same. So in general, duality is only expected when there is a complete decoupling of the supergravity description from that of the gauge theory. So this is a textbook by Johnson where he goes in some detail into this. So like typically this is what you get in ADS-CFT. But that's, of course, a very different type of setup than the one I have discussed. Okay, so then if we cannot do dualities, then maybe the next best thing is to think of this in terms of macroscopics, to think that this black hole description, the supergravity description, well, is maybe not the fundamental description, but it's something that appears at long distances in the macroscopic limit. And that in some way we might be able to regard this as emergent from the kind of more fundamental underlying quantum, underlying string theory. Okay, and there are various suggestions about along these lines in the physics literature. If you look at the way that physicists talk about this, they say things like, actually the Dbrains are the basic sources of the fields, or the P-brain is made of Dbrains, or the Dbrains are located at r equals 0, and so on. Johnson also suggests that the Dbrains could be seen as parts or as constituents of the black hole. So that actually very much suggests a relation of emergence in a way similar to how, for example, materials are made of atoms, and we can regard the macroscopic properties of materials as emerging from the underlying theory of metals, for example. So that might be one way to look at it in terms of an emergence relation of this type. So we go from the Debrain theory at short distances, we go to large distances, and also strong couplings. Now, in the philosophical literature, emergence has often been seen as a matter of basically two things. It's on the one hand dependence, and on the other hand novelty. So it's a definition of emergence that goes back to Butterfield. So the main aspect is novelty, that when we compare two systems, we have one system is dependent on the other. So there is a dependence relation or a linkage relation. But on the other hand, we can also have novelty, or autonomy. So this macroscopic system can be independent relative to the microscopic system that we're looking at. In addition, robustness has also sometimes been added as an additional condition. We won't need to, I mean, for the purpose of this talk, I don't want to go into those details. But let me take this as my working definition of emergence. So maybe the supergravity black hole solution could be seen as emergent from the Dbrains in this sense. So the linkage relation then involves changing the coupling and changing the scales. And so that implies taking a large number of large number of Dbrains, and so that's the limit in which we can actually do the calculation. We get this numerical agreement, and in that limit we get this novel behavior. Namely, we started with a theory where we had no gravity. There were only Dbrains, but there was no gravity. There were only gauge fields, and we end up with a theory where we have no gauge fields, at least no non-abelian gauge fields, and we do have gravity and also some electric fields. So that's the novel behavior. It is also robust in the sense that the properties of the black hole are independent to the details of the microscopic theory, like, for example, the precise location of the open strings on the Dbrain. So it doesn't really depend on that. Okay, so let's look at what do we mean when we talk about emergence. What do we mean by novelty in detail in this particular case? So again, it is not enough to say, well, we have novelty, we have this property of gravity. I mean, that might be one first step towards emergence, but it would be desirable to be able to make something a more precise statement, to be able to say, well, actually, what emerges is actually also, for example, the gravitational field emerges in some way with the Einstein equations that go along with it. So the metric and other fields should appear from this calculation. So, and in some sense, if all these string dualities and approximations that we are doing, if they are all consistent, one might reasonably expect that would actually be the case. Now, is that actually the case? Well, it turns out that there is a good candidate for the metric in particular. So that's a quantity that is called the effective moduli. Well, the metric on the effective moduli space of the Dbrain system. So the conformal field theory of the Dbrains is when you get interactions, it's not a theory on a flat space, but it's a theory on a curved Lorentzian space. So I mean, not the metric, not the space where the Dbrains move, but rather the target space of the Dbrains. So you get nonlinear couplings between the Dbrains, which basically have the property of a metric. That's what we call the Dbrain metric. So from the Dbrain point of view, this is just some effective interaction. It's something that summarizes your, the massive modes of the string that you have integrated out gives you an effective interaction on the Debrain world volume theory, and that has nothing to do with gravity. But if we might be able to reinterpret this as a true metric from the point of view of supergravity. So does that actually work? And to a certain extent, it did work. Now I see that since I'm out of time, I'm coming also towards the end. So, but I won't give all the details. It worked in part, and in part, it worked up to one loop. Let me say it like that. So there was a free field theory calculation. There was a one loop calculation that was done, and that matched. But the two loop calculation, at least initially, disagreed. So the one that goes with alpha prime squared. So it was due to Maldacena in his lecture at Strings 97 in Amsterdam. This also led him to ADS-CFT. So actually, historically, what happened is that he realized that you could describe all of this much better in ADS-CFT. And so, as far as we can tell, no one actually finished or tried to fix that calculation or tried to explain whether there was an agreement or not. And it could be that everybody believes that it would work out. That's, well, in a way, the feeling that you get from the papers. But it could also be that attention just went to the related problem of ADS-CFT, where you could really do these calculations much easier. So ultimately, the natural goal of such a reconstruction would have been to get the entire black hole metric. So now you were able to get only a part of the metric, but not the entire metric. So far as we know, that calculation didn't pan out. This did lead Maldacena to intuit. Well, from the point of view of emergence, that is that you might be okay with that, because in the end, emergence, it tells you that the macroscopic system describes your system to some degree, but of course, when you go probe the system deeper, you may get departures from for example, from equilibrium or. Now this led Maldacena to ADS-CFT. Where you could realize this configuration as a D1, D5 brane system. And that's actually how people nowadays think about this calculation. Almost everyone that looks at this calculation, they look at it from the ADS-CFT perspective. So I come to the end of the talk. So I summarize it in 4 points. The Somen-Javafa result raises a wealth of issues, interpretative issues, conceptual issues that require philosophers and historians' attentions. We have focused on those 2 years between 95 and 97, but there's a lot more to be done. Also, the literature suggests that the relation between the black hole and the Dbrains is not an exact duality, as it is conjectured to be an ADS-CFT. In ADS-CFT, it is conjectured to be an exact duality, but in this case, it isn't. So there is something to be understood there, even at the physics level. We have proposed that based on the evidence, that relation is best construed as emergence of a macroscopic system from a microscopic system as we increase the Toth coupling. So the leading behavior for the entropy and even for the metric agrees, but you might get other disagreements where you might need to start incorporating quantum effects. And then finally, so that's our particular proposal for how to interpret that result. And then again, our proposal is tentative in that sense that if you want to make a definitive statement about the ontology of the black hole states, what are really the black hole states? Are they the states of the supergravity solution, or are they the states of the Dbrains? How are they exactly related? If you want to make a definitive statement about that, obviously you need to know something. You not need to know more about the status of the open-closed string duality in this particular case, which, like I said, is undecided. So yeah, I will leave it here, and I look forward to a discussion. Thank you for your attention.
Thank you. We move now to the Q&A. Again, as previously, to book your just write Q for a full question or F for a follow-up question. So we have our first question from Nicolas. Nicolas, you can do your question.
Okay. Do you listen me? Okay. When we said that black hole could be the same physical system of Dbrains or something like that, this means that black hole is similar to a sort of big brain where energy went from strings, or a sort of like that?
Yeah, that's a good question, because of course that's quite central to how to interpret these systems. So yeah, so here you get a black hole from the 5-dimensional perspective when the system looks really like a point-like system. So it looks like a black hole when the internal space is very small. But even from the supergravity perspective already, actually, if you would probe it at shorter distances, then you would start to see the internal dimensions. So there are these 5 dimensions that are curled up, and then you would start to see that actually it's not a black hole. It's not the Reisner-Nordstrom black hole solution that we get in supergravity, but it's actually indeed a system of P-brains. So it's a stack of some P-brains which normally are flat, but in this case they are wrapped around these internal dimensions, and there are fluxes that there are through these cycles, and that's why it looks like a black hole at large distances. But from close by, it is a complicated system that looks actually much more like this. So that's from this side, and then from this side, actually, the Dbrains are completely flat. So that's important indeed to emphasize that here the Dbrains are curved, here the Dbrains are flat. And that has to do again with the open-closed string duality. So, well, they are flat, or in some cases, they might be round. They might be a perfect sphere. But like, for example, when you have an S1, then it's just a circle. But it's not a complicated. It's not a complicated dimensional system like this one here. So 5 of the dimensions are already gone away. So the theory that we get here is just a theory on a. Sorry, I should say that a bit slightly more precisely. So the internal dimensions are on the internal clavia, but the S1, because it is very large, it is it's flat. So we get a conformal field theory on what effectively looks like a flat space.
Thank you so much.
Okay, next question is from Krishnan.
Hi. Yeah, so my first name is Siddharth. Thanks.
Sorry. Yeah.
No, that's okay. So my question is about the kind of criticism that perhaps Lee Smolin suggested, which was the claim that these models have a lot of symmetry, so there's quite a bit of freedom for you to exploit. So perhaps we shouldn't be too surprised, and perhaps we shouldn't take as too strong an evidence the fact that there are these correspondences between them. Is that a fair summary of that kind of criticism?
Yeah.
Okay.
Yeah.
And I'm curious whether people have attempted to build counterexamples, right? Because if that criticism is right or is on the right track, then one should be able to come up with models which give you the wrong answer. They don't give you the Bekenstein-Hawking entropy. And I'm just curious whether there have been attempts at finding counterexamples, at least somewhat successfully, that show that, say, the Bekenstein-Hawking entropy formula is not reproduced.
Is not reproduced. So there is one famous case, which is the Dbrain. In that case, you do get an area law behavior, but the coefficient doesn't match. So the coefficient is not 1/4. So the coefficient is something else. It's some function of the coupling. And I believe there is a mismatch of 3/4. That is to be expected because that's a system where the supersymmetry does not play a role. So there is less supersymmetry than you would. And so we don't have this protection result. So yeah, even within string theory, there are examples. And I would say that it's quite generic actually, so that if you have some random system where we break a lot of the supersymmetry or even all of the supersymmetry, then we will end up with something that doesn't satisfy, that doesn't have the right counting of states. So there are both cases. You have cases where, like the Kala and Maldacena paper, where they got lucky, and even though supersymmetry was broken, they still got the right result. And then there is the other case where supersymmetry was broken and you don't get the right result. Yeah, but that in a way that is expected. So what I am not aware of is cases where you would expect that there is an agreement and that you don't get the agreement. Sometimes there have been like preliminary claims that there was a mismatch, but then eventually it was fixed. So at least to my knowledge. But since your question focused on the other side of the story, I agree that there are many cases like that. Yeah.
Can I quickly ask a follow-up? Okay, so I mean, to the extent that we consider these kinds of results to be evidence for, say, the claim that string theory is a successful explanation of black hole physics, or at least is on the right track, given that there are many such examples that you mentioned where the right result is not reproduced, should we therefore reduce our sort of credence that string theory is in fact a successful explanation of black hole physics?
I would say that that's not necessary, because from the perspective of string theory, the way that I set up the argument, there isn't a reason to expect that there should be an agreement. So we know that if we break supersymmetry, then these kinds of arguments then don't work, because the calculation, what happens actually in more detail is that as you increase the coupling, you don't have control over the states that you are counting. And so you may get, because we are not counting BPS states in that case, we are counting other sorts of states, right? And so those states are not protected by supersymmetry. So they are excited states. They are not protected by this mass gap. And as we increase the coupling, you don't know which states go where. So you might be counting in one regime, you might be counting one set of states, and in another regime you are counting a completely different set of states. So there is no a priori reason to even expect that this should work. And so that, I think one is rightly skeptical about this working on in cases without supersymmetry. So I think the work that should be done is to better understand why in the Kala and Maldacena case, where it does work, where it is not expected, that in that case, well, why is it working? Whereas, so I don't think that's an argument that that we should lower our credence towards this particular argument for string theory, because there is no argument to begin with. There is no protection, and so there is no argument there.
Okay, thank you.
So next question is from Vincent Stefano.
Mirko, you said Vincenzo?
So, yeah.
Oh yeah, because I didn't have. Okay, thank you very much, Sebastian, for your presentation. I was a little lost in the central part because I do not know sufficiently enough string theory to understand the calculation. But I was impressed by the ontological final thesis, that is that the relation between gravitational consideration, gravitational models of black hole and string theory model of black holes are not a duality, but something more similar to emergence. So in my mind come a well-known example in physics in which we have emergence, and in these cases there are certain typical peculiarities, like there at the higher level there is something new, some new property, and this is the case clearly. At the higher level must be some more physical term that can explain the coarse grain behavior that could be not taken in consideration in the smaller level, and this happens also here. And there must be some bridge law between the lower level and the higher level, and you show to us that in the case of matrix this is possible. But my question is, there are other examples of a bridge law that come from calculations similar to the one proposed by Strominger and Waffa, that could be considered the bridge law between the two levels of Dbrains and gravitational model of black holes. And second, another peculiarity of emergence in physics is also that sometimes explanation in terms of what is smaller can give us the possibility to find something completely new about what is higher. Think, for example, to the Bose-Einstein condensate and other similar examples, which microphysical explanation give us the possibility to find a new macroscopic effect in extreme situations that which are not normal for us, but could be calculated from micro state consideration. Is there something similar also here, or this model by Waffa and Strominger is can only calculate entropy and the metric of gravitational black hole? This is my question. Thank you very much.
Yeah, it's a very interesting set of questions. So your first question about the relation, the bridge laws between the Dbrains and the gravity. I agree that this is indeed a bridge law. The way that we relate the metric on the moduli space to the space-time metric of the black hole. You ask whether there are other examples of that. Yeah, I mean, after Strominger and Waffa did this, people worked out several other similar examples. I mean, all those examples that came out of this are all rather similar. So they're similar types of, Debrain configurations and different types of black holes. So it's often a similar type of system where you can establish these relations. One case where we get something slightly different is when you go to ADS-CFT. So in that case, then the Dbrains basically disappear. They disappear into the background, so to say. and what you get is this kind of dictionary between the on the one hand the Yang-Mills theory on the boundary of the ADS space, the anti-de Sitter space, and the quantities in the bulk, so in the gravity. And for example, the graviton, the asymptotic value of the graviton in the ADS space is related to the curved metric. The curved metric that you get when you are doing Yang-Mills theory on a curved space, for example. And also, if you introduce a stretch energy tensor, the expectation value of the energy tensor of the Yang-Mills theory, that corresponds to a certain to certain excitations of inside the graviton, certain modes of the graviton. So in ADS-CFT there is a dictionary worked out, which you could think of in some sense as a bridge law between those two theories, which is actually more detailed than the one in Stroman-Jarvafa. So that's the main case that comes to my mind. And then about the other question that you asked is very interesting because but I'll try to be brief. It is indeed the case that people started to think of these Dbrains in a quite similar way as we think of, for example, the Higgs mechanism and monopoles. You mentioned superconductivity and, of course, the London effect. There is the analogous of that for field theories is the Higgs mechanism getting massive. Now there are analogies with that where you separate the Dbrains and the open string between the Dbrains is massive. Basically gives you the mass of the kind of Higgs string field, and so you can the way that people nowadays think of these Dbrains is in terms of as solitons in the theory, and so this is reinterpreted then as that gravity in some sense is the effective action that you get when you go from a kind of particle description, you go to a soliton type of description, where the part. I mean, I'm being a bit vague here on purpose, but to kind of build on the analogy, which I think on the analogy that you mentioned, which is actually quite central to a lot of the current work on this. So you could see that the gravity as being a state that is associated with a soliton in the Debrain theory.
Okay, now we have another question from Kirill.
Thanks, Sebastian, for going through this complicated but important material from the 90s and then serving this us on the plate. It was very interesting. I can very well understand how the Reisner-Nordström black hole evaporation motivates this string theoretic approach, in that over the course of Hawking radiation, you deduce the mass, but the charge is left unchanged. But my follow-up question is, how does the string theory community deal with the Schwinger effect? The Schwinger effect, which polarizes the vacuum, which in turn deduces the electric charge. And so is there any natural explanation, just like the one you mentioned, with those open strings, that the closed strings that become open strings, and that's what we see as Hawking radiation? Is there any analog from string theory that gives an explanation of the Schwinger effect? That's essentially my question.
Could you maybe give just slightly more detail about which Schwinger effect you have in mind?
So in the Schwinger effect, you have the vacuum and the quantum field vacuum, where we have virtual electrons and positrons, and then the charge, however, it has, for example, is say positive charge, and then the virtual particles react differently depending on what charge you have, and so the Schwinger effect polarizes as far as I understand it, in a more broad way, that the virtual positrons become electrons, but this has the cost of deducing electric charge from the massive body. So in that case, this would mean you have the black hole charge, and the Schrödinger effect would be deducing charge of the black hole by virtue of the virtual positrons that get excited to real particles, so to say. And so my question is whether in the Schrödinger Buffer or other accounts of string theory, there is a natural explanation of this using a state transition from closed strings to open strings, or a similar effect, which, however, invokes the charge of the string theory, the QF or QH that you mentioned in the formalism.
Yeah. So I haven't looked into this question, so I don't have a definitive answer. But from what you are saying, it sounds like the Callan-Malassina calculation is, at least the words that you are saying, sound quite close to this, in the sense that, so in the Callan-Malassina calculation, we begin with a non-extremal black hole, which has a mass that is higher than the extremality. That has a higher charge. And then we lose some of by vacuum, by basically pairs of open strings that are created in the vacuum. We lose some of them. So the open strings meet up at the horizon, and then they are able to make a closed string. And in that sense, but here it is the mass that is being lost. So I'm not sure about whether there is whether there is an effect of electric polarization. One would have to look at that. But at least from the words, it sounds similar. But like I said, I haven't looked into that.
Okay. We have one final question from Eric.
Okay, so Seb, I have a concern about your proposal that the best way, that at least tentatively, the best way to understand this perhaps is by the relationship between the Dbrains and the black hole is by an emergence relation. I think my concerns are somewhat similar to Smolens and Jacobson's. So let me see if I can try to make it precise. There's I'm worrying about the use of counting measure as the way to calculate the entropy for the Dbrains. Essentially, you can think of the understand correctly as something like an isolated ideal gas. So counting measures is just microcanonical measures, but I guess to be a little bit more precise, since it's an absolute zero temperature system, we're actually counting degeneracies. We're not counting states, but that's. Just put that aside. But the issue is that as we move to the black hole, we're turning gravity on, and it's not obvious to me at all. We're turning on non-trivial interactions, and it's not obvious to me at all that microcanonical measure, that counting measure, is the right measure when you have non-trivial interactions. So, you can't. I don't think it works to justify it by saying, but look, we get the right answer. Because that's begging the question. You want to show independently that you get the right answer without appealing to the fact that you get the right answer. And I know how to justify microcanonical measure for an isolated ideal gas based on physical properties of what equilibrium means for an isolated ideal gas. But I don't know what equilibrium means for the Dbrain system. I'm not even sure that there is a relevant notion of equilibrium here. Perhaps you can comment on that. Anyway, so I guess I'm rambling a little bit here, but I think I basically voiced my concern.
Okay. Yeah, thanks for that. That's a well taken comment. So indeed, the thermodynamics of this relation that is Let me put it on the screen. So let me first say that, I mean, our arguments for why it's an emergence relation, it depends on two things. One, that the entropy is so things that you can calculate give the right answer, but also that you do get the right metric. So the moduli space metric that you derive when you integrate out the massive strings is the same closed string metrics, at least to second approximation that you get within the black hole system. So at least within this rough approximation, we are able to get not just the entropy, but also the right physical properties, such as the metric which satisfies the Einstein's equations.
Does the emergence of the metric, or the way that you can extract the metric, does that depend on the use of counting measure for the entropy, or is that independent?
That's really independent. So that depends on calculating the interactions for the Dbrains, and calculating that moduli space metric after you integrate out all the massive strings.
Right.
So it doesn't really, it's independent from the thermodynamical argument.
Yeah.
So the thermodynamical argument.
I don't think you can use getting the metric as justification for the counting measure, for using counting measuring.
No, I'm not trying to do that. I'm just saying that we don't only have like the discounting argument for the BPS states, but also that the physical system that comes out, at least to leading approximation, is the one that we would expect. So we get the right. Okay. So that's a completely independent. It's orthogonal to the thermodynamic argument that has to do really with the interactions of the Debrain and how that relates to the space-time geometry. So in that argument, there is no thermodynamics involved. Okay. So that's an extra argument.
But can you say anything to motivate why I should be using counting measure when I know that gravity is going to be turned on?
Yeah. So what I can say is this. I would think of it more in terms of, rather than really in thermodynamical terms, because as you know very well, the Reissner-Nordstrom is unstable, right? Its thermodynamics is unstable. You know that very well. So I prefer to think of it in terms of, indeed, just counting states of the Schrödinger equation, the time-independent Schrödinger equation. I count the degeneracy of the ground state, for example. And that number, I know that it is protected by supersymmetry. So there's one thing that we need to assume, namely that the supersymmetry algebra, that's kind of the fundamental. So we do need to have some kind of, supersymmetry algebra at the level of the string theory that ensures for us that there is always, no matter what the coupling is, there is always going to be the same number of BPS states. Therefore, as long as we count BPS states, it's always going to be the same number. That's basically what the whole argument boils down to. If we leave that, then all hell breaks loose. But for the BPS states, that's the underlying assumption.
Okay, thank you.
We also had a comment by Daniel Haro in the chat, which he can do live if he wants.
Well, okay, if you want. I was just saying that you can just define, it's basically what Sebastian said at the end. You can just define black hole entropy in the microcanonical ensemble. You're just counting the number of states that are in some energy band. So we can just agree to be interested in that question. And then that's the question that Strominger and Vance Vafa are trying to answer.
Thank you.